Hi everyone, this is Team 2's presentation of our design for our project number 3 in Engineering Class 131. My name is Henry Ulrich.
My name is Sean Finnan.
I'm Andrew Harsey.
And I'm Truman Parrish. Purdue University is a large campus full of busy sidewalks packed with students moving to and from class by both foot and bike. As a result of this, accidents between bikes and pedestrians are an ever-present threat for both students and employees. Purdue University has asked us to develop a solution to this danger that the community faces with specific requirements. The product must be safe and effective in reducing the number of accidents by getting the attention of bikers and pedestrians. The product also needs to be easy to understand. Confusion will only make the problem worse. The product needs to be able to withstand expectable conditions like constant use and harsh weather. This will be tested through various strength metrics. The device should be easy to implement, which will be measured through time of installation. Inexpensive maintenance is important to any design and will be evaluated through a cost estimation of replacing the parts most likely to fail. As always, cost should be minimized, which will be measured through a calculation using the cost of one unit and the number of units we would need. Finally, the design should fit into the campus aesthetic, allowing it to be effective while not disrupting the landscape of campus.
Before we developed our actual design, we set out to create a list of criteria and constraints that are required for this project to be effective. Some of these criteria and constraints include aesthetics, cost, reliability, and maintenance, just to name a few. To gather data on these metrics, we administered surveys to our classmates to get their opinions on our designs. This became especially helpful in determining the aesthetics and effectiveness of our designs. For testable metrics like cost, we focused on designs that use fewer sensors to achieve similar results as their complex counterparts. For example, we decided our design will only use 3 additional parts of the TI kit configuration. Here are the results from our surveys, and from this, we found that the students prefer the vibrating floor step the most. But after looking into the cost of production, the loud laser seems like the best balance of affordability and effectiveness. As seen here, we found the loud laser to be cheaper to produce than the vibrating floor step.
We're calling the design we settled on the loud laser. We have a housing prototype here. It's been scaled down to reduce costs and improve mobility as we work towards our finalized design. The design we chose features a distance sensor that utilizes sound waves to approximate distance to the nearest object. So it sends a sound wave out this sensor and then it absorbs them back through this one. Ideally, the final product will function with a sensor that uses a laser and light absorption to determine the distance to the nearest object. The product will be placed on sidewalks that feature both a bike lane and a pedestrian lane. When a person walks in front of the laser at a given distance, which would be the width of the bike lane, it will reflect more light back to the sensor. When the sensor approaches a specific point of light absorbed, it will send a signal to the speaker that will emit a high-pitched noise. This noise will alert the pedestrian to move into the lane designated for pedestrians. It does rely on the principle that people traveling on any device such as a bike, skateboard, or any other device to be moving fast enough to not trip the sensor. Here, we have data featuring some of the preliminary tests with the sonic device. When the data has 2 or more data points in a row that are under the given threshold of 3.8 feet from an object, it then emits a beep.
Although the loud laser will be an efficient and working product, there are still a few improvements that can be made to bring it to the next level. One limitation from the loud laser is that it relies on people who are traveling on bikes, skateboards, or other vehicles to be moving fast enough to where they get picked up on the sensor, but not too fast where the sound will be affected. This is basically saying that once a student is moving faster than a certain speed, the loud laser will no longer be able to pick up their movement in time and alert them to watch out ahead. Another drawback of our product is durability. As we know, thousands of students pass through sidewalks each day here at Purdue, and the chances that our product will get stepped on or broken by a student are definitely higher than we would like. A way we could fix this is by adding a few more layers of protective shielding to withstand a little more weight or pressure that's being added onto our product. Although this may affect the aesthetics of the loud laser, this very well may be a trade-off that we have to make in the future.
Thanks for listening.